Continuing with our discussion of relative motion, we will solve a problem. This problem is taken from John Calda's handouts, which is a very popular notes or collection of problems for students appearing for Physics Olympiad. This is the second problem in that handout. So, the question is, two planes fly at the same height with velocities v1 800 kilometers per hour, v2 600 kilometers per hour respectively. Planes approach each other at a certain moment of time. The plane trajectories are perpendicular to each other, and both planes are at a distance of d, which is equal to 20 kilometer from the intersection point of the trajectories. Find the minimal distance between the planes during their flight, assuming their velocity will remain constant. So, we will now have to think about this problem sitting in one of the planes. So, that makes the problem simpler. Instead of doing it in Earth's plane, Earth's reference frame, it is always convenient to solve the problem in one of the reference frames of planes. So, we will do this using the second plane V2, which is moving at 600 kilometers per hour as our reference frame. So, we have drawn a schematic diagram here. Figure 1 shows the distance diagram, that is the meeting point is O here. A starting plane number 1, which is moving at 800 kilometers per hour, will start from the point A and reaches the point O. Plane number 2, which is moving at 600 kilometers per hour, will start from point B and reaches point O. So, we have to find the minimal distance between the planes during their flight. Remember, the first plane is going to reach the point O the earliest. Second one will reach there later on. So, now we have to find the minimum distance between the two planes when they do this maneuver. So, the second figure shows the velocity diagram here. Velocity, so how do we find this? We are trying to analyze the motion of the first plane with reference to the second one. So, as we know that velocity of plane number 1 with respect to 2 is given by velocity of plane number 1 minus velocity of plane number 2. This can be redrawn as velocity of 1 with respect to 2 is equal to velocity of 1, which is v sub 1, plus minus of velocity of second one. That is what we have done here. This is the original diagram. Then in this diagram, this is the velocity diagram. In this, we have reversed the direction of the second plane. So, therefore, V12 is equal to V sub 12 is equal to V1 plus minus of V2. So, the resultant velocity is represented by vector AC in the diagram in the figure 2. So, this triangle, that is AOC, is essentially a 4-3-5 triangle. AO is 800 here, OC is 600, OC is 600, this is 600, and AC is 1000. How do we get that? Using Pythagoras theorem. 800 square plus 600 square would give us 1000. That is, AC square would be is equal to square root of 800 square plus 600 square. That would finally give us 1000, which is 1000 kilometers per hour here. And now we need to find out BC here. We know OC here. OC is 600. We need to find out BC. So what is BC? When A starts from this particular point, it would have reached point O, which is at 20 kilometers from this point. At what time? That which we are now going to calculate that. So we know that velocity is equal to distance travelled over time. So this implies that T is equal to S by OE. So S here is 20 kilometer divided by velocity is 800 kilometer per hour, and this would be equal to 1 by 40, 1 by 40th hour, 1 by 40th hour. So this is time taken for the first plane to reach the intersection point, time taken by plane A, which is travelling at 800 kilometers per hour from this point to reach the point O. By the time it reaches point O, the second plane, which is travelling at the speed of 600 kilometers per hour, would still be falling behind the point O. By how much distance, that we need to calculate now. Since we know that we will do the calculation for the second plane now. This is for the second plane. Again we use the same relation, V is equal to distance travelled over time. This implies we need to know the distance here, distance which the second plane would have traversed when the first plane reaches the point O, which is the intersection point. So S is equal to velocity into time. So velocity is the velocity of the second plane, that is 600 kilometer per hour, into time. Time is 1 by 40th hour. Why we are taking 1 by 40th hour? Because at that point in time, the first plane would have reached the point O here. The first plane would have reached the point O here. So what is the distance travelled by the second plane then? That is equal to, this cancels out, this will be 15 kilometer. So the second plane would have travelled 15 kilometer by the time first plane reaches the intersection point. The second plane would have travelled up to 15 kilometer when the first plane reaches this point O. So it is lagging behind by 5 kilometers. Therefore, this would be equal to BC here in our figure would be equal to 5, and this OC is 50. OC is 50, BC is 5 here. Now this calculation is pretty straightforward, because we have got similar triangles. AOC and BPC are similar triangle. AOC either triangles. Therefore, AO by AC is equal to BP by BC, BP by BC. So this is nothing but we have got AO is equal to 800, AO is 800 and AC is 1000, AO is 800, AC is 1000, BP, which is the perpendicular distance which we are trying to find out, BP divided by BC. BC is 5 here. Remember, the perpendicular drawn from this point, that is point B, on the relative velocity vector would give us the minimum distance between two planes when they travel in this fashion. That is the minimum distance. BP is the minimum distance between the two planes. Therefore, BP is equal to 5 cross multiplying 5 into 800 divided by 1000. So that is equal to 4, obviously this is kilometer. So that is the answer here.